This next section is about two words called the basis and dimension. And let me read this definition here and then we'll talk plainly, okay? If V is a vector space, then a linearly independent set of vectors that spans V is called a basis. So in short, a linearly independent set that also spans is called a basis. All right? And so if I want to show that something is a basis, I need to show two things. One, that they're linearly independent, and two, that they span. Okay, so let's take this. Show that S equals E1, E2, that set is a basis of R2. So what I need to show is that they are linearly independent and that they span, okay? So we've already done the linearly independent thing before. So how does that work? You go by the way, if we remember from before, E1 is the vector 1, 0, and E2 is the vector 0, 1. So A times 1, 0 plus B times 0, 1 equals 0, 0. When we row reduce this thing, it will look like something very magical because it's already done. Oh, it's already done. Look at that. So this implies that A equals 0 and B equals 0. Okay, so that means the trivial solution is the only solution, and so therefore they are linearly independent. Okay, so linear independence done. How about span? So A times 1, 0 plus B times 0, 1 is equal to some vector x, y. Well, when I just look at this, it looks like 1, 0, x and 0, b, y. So what's the solution? Oops, I'm sorry, 0, 1, not 0, b. This says that A equals x and that B equals y. Of course they span, right? Very good. Now, if you get the feeling that this really just amounts to row reducing to the identity, the answer is, yeah, that's really just kind of what it amounts to, okay? It's a little more complicated than that when we run into a set that's a different number of vectors than the dimension of the space we're living in, but since I haven't defined that word yet. Okay. Now, what do examples 144 and 151 say about the set 1, 1 and 1, negative 1? Well, let's go find those here. 144 and 151. Let's go find 144. Make us dizzy here. Okay, 144, the example said, show that these vectors are linearly independent. Good. And the next one was 151. What is the span of these two things? And the answer was R2. Okay, so what does that mean about this thing? It means that S is a basis of R2. Why? Because they're linearly independent. And they span. Okay, so is a basis unique? And the answer is no. No, they are not unique, right? Because this thing was a basis of R2 before, and here's another basis of R2. So a basis is not unique. All right, so what does this theorem say? The next theorem says, a basis is not unique. However, every basis for a vector space will have the same number of vectors in it. Okay, so see that? This has 2 vectors for R2 and 2 vectors for R2. The number of vectors is called the dimension. Okay, of the vector space. And so what is the dimension of R2? We would say that the dimension dim of R2 is in fact 2. All right, so that is a 2-dimensional vector space because there is a spanning set that is linearly independent that has 2 vectors in it. Example 156 says, find a basis for R3. What is the dimension of R3? Well, we can kind of just cheat here a little bit. 1, 0, 0 and E2 is 0, 1, 0, and E3 is 0, 0, 1, I think we can very clearly see that these things are linearly independent, right? This is the only one in that, this is the only one in that, this is the only one in the third coordinate, and they clearly span, right? If you wanted to make, 5, 10, 4, you'd have 5 of these, 10 of these, and 4 of these. Okay, so clearly linearly independent in span. And so the dimension of R3 is in fact 3. Find a basis for Rn. Okay, well, let's define this. So let's say EI is the vector with 0, 0, 1 in the ith spot, and then zeros everywhere else. So then the spanning set is going to be E1, E2, and En. So 1, 2, n, right? So I have n coordinates for Rn. First coordinate, second coordinate, ith coordinate, and nth coordinate. So E1 would have a 1 here. E2 would have a 1 here. En would have a 1 here. Okay. So if I take the collection of all of these, I going from 1 to n, maybe you could say S is the collection of all EI that I equals 1, 2, comma, n. There's another way to write that. Okay, how many vectors does that have in it? Well, it has n vectors in it. So the dimension of Rn is n. I wrote the wrong little curly bracket there. Very good. Find a basis for M 2 by 2, so the set of all 2 by 2 matrices. This is the kind of thing I usually have groups work on, so maybe pause the video and see if you can come up with it here. What is something I want? I want a bunch of things that can add up to the general vector A, B, C, D. Okay, so let's say that my first vector, let's call it, I don't know, U1 is going to be 1, 0, 0, 0. And U2 is going to be 0, 1, 0, 0. U3 is going to be 0, 0, 1, 0. And around that space, U4 is going to be 0, 0, 0, 1. So then ABCD is equal to AU1, BU2, CU3, DU4. They are clearly linearly independent because they don't have any interference in any of their coordinates. And they span. I can clearly make anything out of them that I want to. You might say, this is kind of like just a rearrangement of the vectors of R4, where I just have sort of 4 coordinates and kind of this weird new structure. And the answer is yes, that's absolutely true. So as vector spaces, maybe we can get into this in another day, the vector space R4 is equivalent to the vector space of the set of 2 by 2 matrices. Now, 2 by 2 matrices have some extra structure built in on them, right? And so when I think of two things being equivalent as vector spaces, I only mean in one sense, right? The minute you start adding on more structure on top of it, then kind of things change, okay? So what is the dimension? The dimension of M 2 by 2 is in fact 4. Okay. 159. The set P3 is the collection of polynomials of degree at most 3 in one variable x. So what do those look like? These look like ax cubed plus bx squared plus cx plus d. And I think maybe you can tell what the basis is when you are looking at it. Just kind of thinking about how this is a vector space first. When you add 2 of these polynomials, do you get another polynomial just like this? And the answer is yes. Now the word at most here, the word at most is required. I can't say if I get rid of the word at most, then it's not a vector space, because you could take x cubed minus x cubed, and you get 0. And so I took two things that were both degree 3 and added them, and I got something that wasn't degree 3, but it was degree at most 3. Okay, so that word at most is important here. And if you get rid of it, it's no longer a vector space. So what is a basis? What's the building blocks of this thing? Well, you can see it here. I need the x cubed, the x squared, the x, and we'll call that 1, okay? Although any number would do. So the spanning set is going to be x cubed, x squared, x, and 1. And you can see that these are clearly linearly independent. Again, we'll revisit this linear independence of functions in a later section. But, you know, can you make an x cubed out of x squareds and below with only addition, right? And the answer is no, right? X squared plus x is just x squared plus x. You don't get to bump up to x cubed without multiplying by things. And we don't have a vector multiplication in vector spaces, right? Remember that. We only have scalar multiplication and vector addition. So these things are linearly independent. They definitely span. You can see it right there. And so what is the dimension? So the dimension of P3 is 4. And I might challenge you, what is the dimension of Pn? Well, what's the relationship between those two? For 3, I need 3, 2, 1, 0. It's going to be n plus 1. I'll let you think about that some more. In summary, here's kind of what we've learned so far. Okay, here are the important words. We got to know what a vector space is. Very importantly, what linear combinations are, and how linear independence, span, basis, and dimension all kind of work together, okay? If you understand linear combinations, then the span is really just the set of all the linear combinations. Linear independence is when you have vectors that can't be made out of linear combinations of themselves, right? Basis is when you have a linearly independent spanning set, and the number of vectors in a basis is called the dimension. Okay, so these things kind of all get along in a very good way. Now, I think the next theorem on the last page is a good way to kind of wrap up these first 4 sections. And it's sometimes called the 2 out of 3 theorem, and it goes something like this. Let V be a vector space, and let S be a collection of vectors in V. Okay, so I've got n vectors in V. If 2 of the following are true, then the third is also true. Okay. Number 1, S is linearly independent. Number 2, the span of S is V. And number 3, the dimension of V is n. Okay. So if I have 2 of these, then I get the third one for free. I just kind of want to just talk through this, although I wrote the proof there if you want to kind of think about it, but I'm just going to kind of think kind of plainly here. So the first one, 1 and 2, are the definition of a basis, right? So if you have a basis that has n things in it, then the dimension's n. So the first one is really just by definition. What if I have n linearly independent things in an n-dimensional vector space? The idea is if you have n linearly independent things in an n-dimensional vector space, there's no room for it not to span anything, okay? So if you think of something like R2, if I have 2 vectors here in R2, is there any way for me to have some other rogue vector over here that you can't make out of those 2? And the answer is no, right? There's going to be some linear combination of those 2 things that I can make, right? If you're into physics, then you can think of everything as the vertical and horizontal components. There's nothing living in R2 that you can't make out of the I and the J. I just said that backwards, but you get the idea. Okay, there's nothing living in R2 that you can't make out of those. All right, so if I have n linearly independent things in an n-dimensional vector space, it has to span the whole thing because there's no room for anything to get away. All right? Last but not least, if I have an n-dimensional vector space that spans, so I've got n things that I know span everything, then they have to be linearly independent. Okay? Why is that? Well, because they hit everything in the vector space that was n-dimensional, and they are n of them. right? If I were short, if I had one less, then I wouldn't be able to span the whole thing, right? So if I have n vectors that span an n-dimensional vector space, then they've got to be linearly independent, because if they were not linearly independent, I could toss one of them out and toss out whichever one was a linear combination of the other ones, and that would give me one less dimension here, but it would still span, so it would be dimension n minus 1. Okay, I think that's basically what I said down here in this proof, but that's kind of what's going on here. And you can think of both of these things as kind of, if you think of these as in R2 or R3, then it can be very helpful. Okay, if you got any questions on that, please come by and ask. I think this theorem here really is kind of at the heart of all the stuff that we did in these first 4 sections. Okay, and I'll see you next time.